All right, welcome back everybody. So here's our next lesson. So today we're going to look at the trigonometric graphs. All right, so here let's take a look at our section. So there's three key objectives here. We're going to look at how to graph sine of x and cosine of x. Then we're going to talk about how to graph transformations of these functions. And then at the end, we'll talk about a graphing app called Desmos and how to graph functions responsibly and ethically. Okay, we'll save that for the end here. So just as a reminder, you can always grab our class notes from our Canvas page. You can download it right here. These are the blank notes, and I do encourage you to print them out, keep them nice, organized in a nice folder, and then you're going to have basically a nice little textbook when you're done with the course. Okay, so let's switch some gears. Let's go to actually give me 1 second. All right, let's go to these notes here. All right, so the first key point here is that we are going to look at the graphs of sine and cosine. So remember in our last lesson, actually let's just take a quick look at that. Let's go all the way back. So the unit circle perspective. So we defined sine, cosine, and the other trigonometric functions as follows. If you give me a real number t, remember we're going to think of this as a radian, and a radian is a measurement of arc around the circle. I keep calling this the wet noodle because it's literally a length. Okay, once you're given that real number t, then you draw the arc, and then the terminal point is the red point P where you land, and you end up. That gives you a point, which means you have an x-coordinate and you have a y-coordinate. So the x-coordinate is called cosine of the number t. A little bit tricky, right? Because we have the x variable is also a function of the variable t. Now the y-coordinate of the point P is going to be our sine function. So we're going to focus on just these two functions here. All right, so first what I'd like to look at is the following, and there's a link to this in our notes, so you can actually investigate and play with this yourself to gain a lot of great intuition, because what is happening in trigonometry is things are really moving and they're very dynamic. All right, so check it out. So we got our unit circle here in blue, dashed blue, and check this out. So right now what I want you to focus as, there's gonna be a lot of stuff moving, but I want you to focus purely on the unit circle. So I'm gonna move the slider that it's actually a Greek letter alpha. And look what happens. Focus purely on that blue point. So the blue point is moving around the unit circle. There's one wrap. There's only two full revolutions. And in fact, you can check. So if you look at the Desmos app, it'll say it went from 0 all the way up to 4 pi. And if you remember, the unit circle has length 2 pi. So if I do 2 full turns, that's going to have length 4 pi, which is a little bit off of the screen because here is 2 pi. All right, so let's do this again. Keep in mind, just look at the blue point. As I look at the blue point, all that you're keeping track of is just a point moving around the unit circle. All right, now what I want you to take a look at is, well, I always like to start with cosine first. Cosine is, remember, the x-coordinate. So as you look at this blue point, and as the blue point starts to go up, the x-coordinate starts at 1, but then it's going to actually shrink to 0 because as the point goes up, the x-coordinate actually gets smaller. Check this out. So I'm going to try to go slow as I move the point. So see how the blue point is moving up? And the x-coordinate is getting tinier. And now the x-coordinate is at 0. Now the x-coordinate is negative. Now the x-coordinate is at -1. Right around here. Okay, now let's start this again. notice that there's this purple point, and if I actually click on this cosine animation, you'll see that it's actually in purple over here. So I can actually hide the point. You can see the point is blinking because I'm clicking on this little purple thing. So cosines are purple. Okay, so let's run through the animation again. As I start at 1, notice that the point is actually has high y value 1. And as I move, it actually is going down to 0. Notice that the cosine of the terminal point, the blue point, on the circle, the x-coordinate is at 0. But that just means that the y value has dropped down to 0. And then what happens is as you kind of follow it, you can kind of see the orange lines are here to guide us. And now let's do the whole animation again. And notice that the signs are actually going to be green. So this is kind of a cool picture. It's showing both of them at the same time. And look at the green one. The y value is sine, and notice that the y value starts at 0. So that's why this green point starts at 0, 0. As I increase a little bit, the y value is actually going up. So the green is going up. Y values are still going up until I hit about here. The y values are at the biggest they're going to be. They're going to be at 1. But then I start actually going down in the y value, and then the green is going down. So you can see that the y values have kind of like this little hump because the y values go from 0, they go up to 1, and then they come back down to 0. And if I actually keep going, the y values will become negative. And then you can see that we have a little hump, but in the negative side. All right, so in a nutshell, those are your sine and cosine functions, but we're going to break it down into a lot of detail. All right, so let's go to our 6-3 notes here. Okay, so again, here you can see that in these notes, there's actually a link to the demonstration so that you can kind of look at it yourself. All right, so what is going on here, let's kind of, before we jump into it, do things by hand. I really love this animation. You can see it on canvas moving, but here's just a screenshot of it. Is basically, you can see that the corkscrew or helix looking curve, that is going to be our t. And then we're going to have, actually let me draw it here, we have this kind of wiggly curve in blue. This is our cosine function because those are our x values. We also have this squiggly red piece that are our y values. You can see y here, x here, and the way this is drawn. And if I look at this kind of squiggly thing, this is our t value. So as the t's are getting longer, we're drawing our sines and cosines. Now what's kind of neat is if you look at this picture carefully, it's very hard to tell the red from the blue, right? They look almost identical, and that's not a coincidence. In fact, sines and cosines are the same shapes of curves. The only difference is that one of them is shifted than the other one. So they're actually the same. So we'll prove that a little later. The other thing that's interesting is because once you've done a full turn of the circle, you're basically going to repeat the same picture the second time that you do the turn, third time, fourth time, etc. Or even if you go backwards. Once you go backwards, you're basically repeating everything in reverse. This is a property that we call in math periodicity. Okay, periodicity. We say that the period is p of a function, and I didn't like how it kind of wrote it in 2 lines here, so I wrote it again. If we have any function that has period p, it has to satisfy this property. If I add t and p together, it's the same value as if it was just at t. Hard to wrap your mind around that, so don't worry too much. We'll build our intuition by thinking purely of sine and cosine. Okay. So, I've already kind of sketched this out a little bit so that I don't have to do all the boring kind of drawing the grids here. First things first, we are going to plot y equals sine of x by hand. Okay, keep in mind the notation convention is that we are using radians. So what we're using is, it's kind of a little confusing where you're actually plotting the t-axis along the x-axis. So that's going to be really, really crucial. Now, whenever you need to plot the graph of something, we are going to do the following. We're going to put the x-coordinate will be the t variable. The y-coordinate will be sine of t. Okay, so to plot a function, it's usually helpful to plot a few points. So I've already got a couple angles here pre-selected: 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's just quickly review where these angles are. So let's maybe use purple here. So 0 is over here, pi over 2 up here, pi on the left, 3 pi over 2 on the bottom, 2 pi, we're back to where we started. So notice that I'm actually skipping over all the special angles on the whiskers, and you're going to see why in just a second, that I actually do want to skip over those. Okay, now for the y, now let's evaluate sine at these values. So we want to evaluate sine at 0, sine at pi over 2, sine at pi, sine at 3 pi over 2, and sine at 2 pi. So, since we did two big lessons on how to evaluate on the unit circle and also how to evaluate the sine functions, let's just go through it step by step. So, if I'm at 0, remember sine is the y-coordinate of this point. What's the y-coordinate? It is 0. Okay, great. Let's go to the next one. Next, I'm going to go to pi over 2. The coordinates are at 0, 1. Now, sine of pi over 2 would be the y-coordinate, which means we're going to put 1. Cool. So we've got two values. Next up, pi. Okay, so pi is over here. What's the y-coordinate? The y-coordinate is 0. And 3 pi over 2, what do we got? -1. And then at 2 pi, we're back to where we started with the y-coordinate is 0. All right, so you know what I'm going to do? I'm actually just going to highlight, or let's point with red arrows, because again, we're looking at the y-coordinates for sine. All right, so now what we're going to do is, remember, we're plotting the x values the same as the t values. So what we are going to do is, I basically like to notice there's no scale on my x and y axis yet. Whenever you're drawing the trig functions, you basically save the scales. How you're going to, the scaling just means like how are you measuring distances. You save that for last. So what I'm actually going to do is I'm going to do where I put 2 pi over here, because I know that all I need is from 0 to 2 pi. It's going to give me one full complete graph of sine, and then it just repeats itself from here. The other thing is, notice I've cut this up into basically 4 pieces. I'm starting at 0, then I go 1/4 of a circle, 1/2 a circle, 3/4 of a circle, and then finally the last point. So it's kind of pretty interesting geometrically that we're thinking of it this way. So let's cut it in half at pi, cut this in half again, will be at pi over 2, and then cut this one, which we know is 3 pi over 2. Okay, so that's actually a very important point, that you start with 2 pi. I'm out of the camera, I'm not used to it. 2 pi is the full interval, and then we cut it into quarters from there. All right, now, next piece is, how do we want to scale the y-axis? The y-axis, well, we actually have to look at what kinds of numbers are we getting here. So we're going to need to plot 0, 1, -1. That's only 3 values, actually. Okay, so I'm going to plot them from basically -1 to +1. Now, let's try to sketch these somewhat accurate to scale. So remember, pi is approximately 3.14. So if you divide that in half, it's about 1.57. So that's already, so from 0 to pi over 2, it's already 1.57. So if I'm going to be try to be somewhat accurate, I'm going to maybe label my 1 and minus 1 like this. All right. Now let's plot some points. At 0, so let's see, at 0, the y value is 0, so let's plot a point here, 0, 0. At pi over 2, our y coordinate is 1, so we're going to go up to 1. At pi, we're going to be at down to 0 again. At 3 pi over 2, we're at negative 1. Going to look a little funny. And then the last one, back to 0. So even though, think about it, as we go back in the unit circle, we're back to where we started. When we're drawing it in this way, because the x value just keeps moving to the right always, we're back to the same value, which is 0, but we're actually in a different location. So the next thing is, well, okay, so we have 5 points here. So, and we go from 0, we go up. Gosh, I'm so bad at like being on the middle here. All right, go from 0, we go up, then we come back down, then we go to the negative direction, and then we go back up again. All right, so since I showed a nice graph of these here, we know that these have kind of a nice curve here. This is the better representation. So let's try to mimic that. So we're going to go up, and I like to think of it as kind of like a little hump. And then I have that same hump but upside down. There is our graph of sine. Now, what's kind of interesting is, well, I just drew it from 0 to 2 pi. However, a big key point about sine is that it actually goes for forever, and it'll just keep repeating the shape. So what I always think is really important is that you actually don't, not everybody follows this convention, but I always like to draw it as a curve with arrows. So let me put a little kind of draw arrows. So why do I want the sine function to have arrows? Well, it's because the the x values, which represent how many times we're wrapping around the circle, we can do that as many times as we want. We have the whole real numbers as our inputs. So what this represents is it just means that this continues even further, and it continues to the right. That's why I have a green part going that way. But it also continues to the left in the negative direction. We're not going to do it right now, but it does. So that's why I like to put the arrows, because it means that it's going to continue. I have also this little note here where it says don't. So what did I put here? So let me just uncover it. So since we actually looked at a nice animation of the graph of sine, we already knew that it should be nice and curvy, right? So don't draw something jagged. Remember these 5 red points. Don't draw something like this, because that's not the shape of sine. Also, don't go really exaggerated in the wavy direction either. It's kind of a very unique shape. It's like a little mountain, like that, little hump. Okay, so just, this is my advice of just, again, I've been teaching trigonometry for a long time. I've seen students draw all sorts of really poor graphs. So I'm pretty strict about this. So try to draw it really pretty. Try to really pay attention to exactly the right shape of the curve. All right, fantastic. And then what was the other big green thing that I put here as a note? Okay, so I labeled my axes. So I have my x, my y. I scaled my axes. You can see I have the x markings, and I also have the y markings. I added the arrows, so that's this green part here. Of course, if you're just doing it in one color, you would draw all of this in one color. I like having multiple colors though, because it really helps everything pop, and it really conveys a lot of extra information. Okay, and usually the tip is include at least one full period, because the shape will repeat itself. But if you draw one full period, you're good to go. All right, great. Now we are going to do the exact same thing, but for cosine. And I'm going to go a little bit quicker here, but not too much quicker. So for starters, remember we're going to plot points, and we're going to plot the t is going to be the same as the x. So we're going to be moving in radians in the t-axis. The y is going to be now cosine of t. So as we kind of, let me zoom in a bit, we're going to evaluate, well, what's cosine of 0, cosine of pi over 2, cosine of pi, cosine of 3 pi over 2, and cosine of 2 pi. So as before, we go to our unit circle. We're going to use these key points again, and let's just evaluate them. So cosine of 0 is the x-coordinate of our first point over here, so that's going to be 1. Moving to the next point, cosine is now 0. Moving to our third point, cosine is going to be the x-coordinate, -1. Next point, cosine of 3 pi over 2 is going to be the x-coordinate, which is 0. And then the last point, we are back to where we started, and the x value is 1. Okay, so we've got our values. Now time to go to our xy plot. And I like drawing them by hand. I know that I can make it look prettier, but I do find the hand-drawn stuff is way more powerful, because it really, you know that you drew it, and you know that you're trying to convey information for other people. And when you look at just like computer-generated stuff, sometimes it's just super boring, and it's easy to tune it out. That's why I like drawing things by hand. That's why you're going to see me do all the notes hand-drawn, because I think it's very powerful. All right, so time to scale our axis. So again, we're going to do one full turn of the circle. So we're going to plot this through 2 pi, cut this in half, pi, cut that in half again, and then this is going to be our 3 pi over 2. Okay, so as before, 1 and -1 should be somewhere around here. Now to plot the points. I'm going to do them in red. So first point we plot is 0, 1. So we're going to start over here. Next point we plot is pi over 2, 0. So we're going to go down to here. Next, we're going to be at pi -1, so we're going to be down here. At 3 pi over 2, we're going to plot 0, so we go back up. And then finally at 2 pi, oops, let's try that again. 2 pi, we are at back up to 1. Okay, so notice that where we started, which was at the y value 1, we're going to go down, then up, and we end up at the same y value. So again, just like I drew some don'ts, don't make this a v. This is not the right shape of cosine. Very, very bad. So let's delete that. Remember, this is a nice smooth curve. So this one's a lot harder to draw, and sometimes I'll take like a really light pencil and I'll kind of pre-draw it, and I'll even draw a little bit extra, because it's like I'll kind of spill it out. And that's pretty good, actually. So now I'm going to go back through with my red. Okay, there we go. That looks pretty good. And in fact, let's, through the magic of drawing digitally, I'll remove my kind of training wheels. So that's cosine. And it's kind of funny, because where we're cutting the shape, it looks kind of like this little bowl. But actually, if you go up here, and if you were to kind of keep going for the sine, and if you look at the piece right here, it's the same exact shape, or they should look the same. Okay, remember how I said that sine and cosine are the same, basically? This is what we're experiencing, and it's kind of a hint to that. It's the same, but it's actually moved, right? The purple part does not line up on the same part over here. It's actually moved to the right a little bit. All right, cool. If you want to do that same trick with cosine, like where would you move it to get to sine? Actually, if you continued the shape and you went like this, notice there's your sine curve, right? It's actually same as this piece. It's just shifted to the left a little bit, and I actually have to start at a little bit of the negative values. Okay, cool. So there's our graph. As before, there's my full period, but I like to actually keep it going a little bit, and for the cosine, I like to just kind of go down a little bit, because again, it'll go up, and then it starts to come back down if I extended it even further. All right, as the last picture, I'm going to put this little note to draw arrows. And just to add a nice little touch, I'll even label the graph here. This one was y equals sine of x. This one was y equals cosine of x. So why did I use t's? So if you kind of go back to the original construction here, I used t's as kind of a temporary value here, just to kind of help our thinking to going from the unit circle to these graphs. But at some point, we kind of just start blurring the lines, and we start leaving out some pieces of information, because if, we're going to add new things, and if I have to start by drawing a unit circle talking about, the wet noodle every single time, the videos would be even longer than they already are. But I'm trying to go a little bit slow for these first few lessons, since I really want to emphasize the really key points over and over again. Okay, so there we go. I want to maybe talk about one more thing before I move on to the next piece, is what about the whiskers? Let's do them in purple. So we actually know the coordinates of these special angles, right? We have the special angles would be pi over 6, pi over 4, and pi over 3. And we have both x and y coordinates. That was one of the really big results from our first lesson, right? We actually proved that these had to be the coordinates, which is, very exciting. We know where everything comes from. But, what these don't help you draw the picture too accurately, to be honest. Let's look at our sine value. And let's do maybe pi over 4. So pi over 4, if we're doing sine, it's going to be root 2 over 2. So let's pull up the calculator for just a second. All right, so we got our calculator now, and I don't know what I was working on, so let's clear it, and let's do root 2, so second square root, and then let's hit the right arrow so that I leave the square root, and then I'm going to divide by 2. Hit enter. So it actually just gives me right back to what I typed. It just makes it look a little nicer. Sometimes you'll hear me call this pretty print. That's not what I want. I don't want the simplified answer. I want the decimal. So I'm going to hit, remember, you saw me talk about this in class. This double arrow is super helpful. If I hit that button, it'll give me the decimal approximation. So about 0.7. So what does that do for us in terms of this picture? Well, what that means is pi over 4 was right here, right in the middle between 0 and pi over 2. And what that means is if I really wanted to try to draw this really accurately, right, this purple point here, the y value would be at about 0.7. And then if you were to try to even do the other whiskers, which I'm not going to even try to do accurately, you would get a couple more points here. Excuse me. But again, you can see how for this purpose, it's not really going to be helpful to give you an accurate graph. What the key point in drawing these is the kind of the qualitative description of these graphs, like what are they doing? So for us, if we really want precision, we just take out the calculator, and hopefully now you really understand what you're asking the calculator to do. But in drawing these pictures, you really want to know, okay, the graph is going up, and then it comes back down, and it has this beautiful wave property. So that is kind of like the really key point about these functions, and they just show up in nature all of the time. This is why we're studying them in such detail. A lot of applications in science have this kind of up and down periodic behavior where it just does this repeatedly. So that's essentially the phenomena that we are looking to study. All right, let's actually get rid of the calculator. All right, let's continue. So what's next? Let me zoom in a bit. So next, here's just, a nicer version of these graphs. And the other thing to keep in mind is that they go for forever. One thing I do want to add to these pictures, and let's do it in bold yellow, is the little arrows. Our textbook doesn't have them. Not every book forces this, but I think they're really, really important. The little arrows are really an indication that they go for forever. All right, next I want to just review a little bit of transformations. So first section is just a bunch of review, and I've already just drawn some pictures here just to remind you of these concepts. So I'm going to have two functions here. The kind of f, which is just whatever this squiggle is. If this is f, then if I look at a new function g of x where I add a constant, that's just going to vertically shift my graph, either up if a is positive or shift it down if a is negative. Okay. The other type of shift is a horizontal shift. Now look very carefully at this formula. Instead of f of x plus a, that's if the plus a is outside of the parentheses, then it's a vertical shift. But if it's inside of the parentheses, we actually have an extra minus sign that's part of the notation. This is super trippy, and I remember thinking when I was a student, this would always trip me up. And here's the reason why we actually add a minus sign. Because of basically, if we're going to make the a positive number, then a positive number should signify a shift in the positive direction, which is to the right. That's why this blue curve is to the right of f, because I say, hey, a is positive. If a is negative, then we're going to shift to the left because that's towards the negative direction. Okay, so that's why we actually have that extra minus sign. Now, for the vertical shifts, it's already correct because if I add a, that means if a is positive, I am adding vertical height. And if a is negative, then I'm subtracting vertical height. So I basically move towards the negative y-axis if a is negative. If a is positive, I move towards the positive. All right, so I'm not going to go that slow through all the other ones, right? So hopefully you remember a reflection. If I have f here, I can reflect it across the x-axis by making all the y values opposite, or in this case, negative of each other. I can do a horizontal reflection by putting a minus sign inside of the parentheses. So if this is a piece of f, if I put minus sign in the parentheses, I would get it reflected across the y-axis. Now, the horizontal dilations are the really tricky ones. So that really means you're either taking your graph and you're stretching it, or you're pushing it or compressing it. These are much harder to study, and we'll just study those in the context of the trig functions. This was just, sorry, I just copied an extra graph here, so ignore that. All right, so let's take a look at the next example here. And the first two are not too complicated. What I want you to do is pause this video, see if you can think about what the graphs should look like. So for part A, it says y equals sine of x plus 1, the plus 1's on the outside. So I've already kind of gotten a graph of the original sine, right? This is sine of x. It's okay if you don't have it memorized yet, but I really do want you to try to memorize the graph of sine and cosine soon. Okay, what do you think is going to happen? Pause the video, think about it. Okay, well, here's the answer. Plus 1 is going to be a vertical shift, and we're going to shift up. Okay, so we're going to vertically shift up. So, whoa, what happened here? Oh, it's because I copied one of them. So you can see the red. Oh gosh, this isn't working as I intended. All right, I'm just gonna leave it. I don't know how to fix it in a more aesthetically pleasing way. Let's see. That's moving everything. Okay. How about this next one? We're just gonna have to deal with this weird double graph. If I have a minus sign in front of my function, that's gonna take all the y values and flip them across the x-axis. So maybe what I'll do is I'll just draw it like this. So notice that I flipped it, right? If my y values are positive, like in this little hump here, the y values are positive, then I make them negative. So that's why I draw it down here. If my y values are negative, then by multiplying it by minus sign, it makes them positive. So it basically does this type of thing. All right, let's see what happens. Maybe, nope. All right, you know what, maybe, maybe I'm just gonna have to add new graphs here. That did not work as intended. I can uncover that though. All right, let's see. How about this one? This one is a vertical shift up. So I'm just going to move everything up. There you go. Excuse me. Okay, so those are two really easy transformations. Some of the tougher ones are going to get a little bit tougher now. All right, how about for this one for cosine? Y is 2 times cosine of x. So this is a dilation here, where we're actually going to stretch it. Now, this 2 in front of the cosine is telling us we're going to stretch the y values by 2. Okay, now some of those values, though, aren't actually going to stretch at all, because 0 times any number stays the same. So anytime we're at 0, those stay exactly the same. Now, if I have y is 1, then I'm going to double those. So I'm going to actually stretch those over here. And if the y value is negative 1, notice I'm looking at just the y value here. Negative 1 times 2 is actually going to stretch it in the negative direction. So what we're going to get is we're going to get kind of a stretched out cosine. So that's what 2 times cosine of x looks like. All right, and then the last one here, what if we have cosine of 1/2? This time, oops, let's go ahead and uncover this. It's a stretch by 2. This time, multiplying the x by 1/2 inside of the parentheses. This one's kind of weirder. It's actually compressing the x-axis by 1/2, which has this interesting effect. I'm sorry, it's actually stretching out the x-axis. So what happens is, remember the period of cosine was 2 pi, and as we did from 0 to 2 pi, we would get back to where we started. Well, if I have this 1/2 here, basically to get back to 2 pi, I'm going to have to be plugging in 4 pi. So what it actually does is, at pi, so here's the original graph, right? Basically, by the time I get to pi over 2, I'm only going to do just this piece, but now it's going to be stretched out, so it's going to look something like that. So let's draw it like this. And this is going to be at 4 pi. So it basically stretches out, but along the x-axis. All right, and let's put a little bit, let's put our arrows here. So cosine got stretched out that way. All right. Next up is really just a summary of all the different transformations applied to sine and cosine, and we're going to give everything some special names because these are used a lot in the sciences. So they kind of got special names attached to it. So we're going to call the number in front, remember that was a vertical stretch or a vertical compression. We're going to call that the amplitude. So the amplitude's down here. You can kind of see it right here. Amplitude is going to be the absolute value of this number. Okay, so the reason why we do the absolute value is because we're only grabbing just the positive part of it. Okay, so when the a value is bigger than 1, we think of this as a stretch because the y values get bigger. Okay, think of them kind of like waves in the ocean. The bigger the amplitude, the bigger the wave that you're going to ride. If the a value is smaller than 1, then it's going to compress the wave, make it tinier. Now, if you like music, really big, actually no, the amplitude isn't so much. So for waves, the amplitude is kind of like the loudness that we hear. All right, what is the next key number? We're going to use this k in front or inside of the parentheses. So we're going to give that a name as well. Actually, we don't give that a name, but it's related to a name. Now, remember what the k does in front of the x is it either stretches or compresses the x-axis. So we're going to call this a horizontal shrink if k is bigger than 1, or a horizontal stretch if k is less than 1. Remember the example we just worked out? We kind of just reasoned that, okay, we had a 1/2 here. It stretched it out because the period is now 4 pi. And remember the reason for that. It basically, I'd have to plug in 4 pi before cosine kind of cycled through again. Okay, let's see. Am I missing anything from these key terms here? Yes, there's the box with the star. So with these functions, basically, let's go back to this example here because this one's really interesting. So basically, it takes us 4 pi before we repeat the pattern for this example up here. So what that means is the full kind of pattern, we call that the period. So for the normal function, this one repeated the pattern from here to here. Even though it was stretched vertically, it still kept that 2 pi. So there's a formula that's really helpful to remember that tells us the period of a function, of the trig function, sine or cosine. We use capital T for period. That's just traditional. And the formula is just this. It's 2 pi divided by k. Let's think about our example here. So if we apply that formula to this one, 2 pi divided by, now the k is 1/2. So I'm going to divide by 1/2. If you remember your algebra, right? If you divide by a fraction, you do the flip trick. You flip it. And we actually end up getting 4 pi, as we thought about previously. So that's great. We have kind of 2 different ways to think about it. All right, so let's look at the next examples. And hold on, I have to sneeze, so I'm going to pause the video for a second.